From now on, let's implement optimized CBOW and SkiCram. First of all, we are going to implement CBOW. The first method we need to implement is, of course, the initializer. Bucket size, hidden size, window size, and corpus. And we do basically the same thing. We first need to initialize the weights. BH, F, and W out. HV, like this. And the next step we need to do is creating layers. Self in layers or are in range. Because here we are receiving window size as a parameter. We are going to create multiple in layers. So 2 times window size, because we are considering the left context and the right context. And layer comes. Here we are using embedding rather than matrix multiplication, because when we do matrix multiplication, it was like one hot embedded word vector times vocab size, hidden size, like this. However, we don't have to do this matrix multiplication. This is quite expensive. However, the only thing we want is just one row of that word vector matrix. And we are going to avoid that situation by implementing this embedding layer. And I'm going to talk about what this embedding layer is about shortly. And self in layers layer, like this. And the next modification we are going to make is the loss. Rather than using the softmax loss, we are going to use binary logistic regression loss. And to do so, we are going to define something called negative sampling loss. Negative sampling loss. And this one receives W out and corpus and the power and the sample size. Sample size. And sample size means the number of negative samples we are going to sample. Okay. All right. And the next step is we collect parameters and gradients. Layers self in layers plus self negative sampling loss of self params and self grads. And we collect all the parameters from the layers and all the gradients from each layer, like this. And for external usage, we're going to store word bags like this. And how do we implement the forward method? How do we do this? We first need to receive the context and the target. First, calculate age, initialize age as 0. And what we are going to do is iterate through all the layers. And what we are going to do is the context embedded as this layer and add them all. And take the average like this. Okay. And we calculate the loss using negative sampling loss and forward. And compare the value with target. And this negative sampling loss automates comparing the score and target inside. We don't have to calculate the score by our own, and we just pass H and target, and this negative loss will handle all the rest of the jobs. And we just return loss. Okay. And we also need to implement backward. We first need to pass this value to NS loss, D out. And after receiving D out, we need to distribute this D out to NH. And we take division here, like this. Self-in layers, we just pass this backward gradient, and then we return none. This is the implementation of improved version of CBOW. And to complete this implementation, we need to implement embedding and negative sampling loss. Let's do embedding first. How do you implement this embedding? It's quite easy. We receive the parameters like this. And our params, we store our weight. And for grads, MP0 like W, like this. And we need to keep track of the ID. And why do we need to keep track of the ID we are taking? When we implement this forward and backward method, it will be clearer. We first receive our parameters. Rather than performing matrix multiplication, what we are going to do is just sample the row from at this IDX position, and we just return out. That's all. We don't have to do matrix multiplication. And this greatly reduces the computation, the amount of computation. And how do we implement backward? We first get the gradients, and other parts have not contributed to the output. Therefore, we put 0 there. And at the position where we sampled the word vector, we pass the upstream gradient like this. Okay, so this is quite simple. And the next thing we need to implement is negative sampling loss. You also need to implement the initializer, corpus, power, sample size. Self, sample size, sample size. And here we are going to use something called sampler, unigram sampler, corpus, power, sample size. I'm going to implement what this unigram sampler looks like shortly, so don't worry about that. Loss layers. Here, we are not going to use softmax loss. However, here we are going to use sigmoid with loss because we are using binary logistic regression rather than multi-class classification. We're just using sigmoid with loss. Or the number of sample. And here we are going to introduce another block that is embedding dot. This sigmoid with loss calculates loss rather than just calculating the sigmoid function. And embedding dot does similar thing. Rather than just calculating or returning the word vector we want, it calculates some values. And I'm going to show you what this is doing shortly. And the next thing we need to do is collect parameters like this. Okay, then what is the forward? As you can see here, negative sampling loss receives the encoded word vector or the average word vector and the target. Now what we need to do is compare the target after make a prediction with this H. That's for positive samples. And we also need to do that job for negative samples. Therefore, we need two jobs. We first need to check target size, how many batches we have. And we need to pass the target because we don't want to sample target for target. That's why we're passing target here. And forward for positive pairs, we first need to calculate the score. And embed dot layers forward H target. Because here, we're getting just one target score, okay? And the correct label is just once. And the first one compares the score and the correct label. And forward for negative pairs. Because we have one target but multiple negative pairs, we need to do some loop here. For I in range self negative sample size negative target negative sample at the ith position like this. The score is going to be self embed dot layer 1 plus I, because the first one, 0, 1, the 0th one, was used for the positive pair. Actually, we have just one pair here for the positive pair. Okay. However, we have multiple negative pairs. Forward, H and negative pair, negative target. And we add up the losses, self plus layers, 1 plus I, forward, score, and negative label. And we return loss. And how do you calculate the backward? Simple. We zip loss layers and embed dot layers. First pass that D out to L0 loss layer, because loss layer is the first one we encounter when we go backward. And then the next layer is embed dot layer. Okay, so the last loss layer, the last embed dot layer, and the next thing we need to take care of is the second last loss and the second last embed dot layer. So that's why we are looping 4 here. Okay. And DH plus L1 backward D score like this. And we return DH. Okay, that's the implementation of negative sampling loss. And what do we need to talk about? The next thing we need to talk about is embedding dot. This is quite similar to embedding. Embed is done through embedding, self params, self embed dot params, self grads, self embed dot grads, self cache. We need to keep some values for backward propagation. In the forward, we first get target W, IDX, and the output is going to be target W dot H. This is actually dot product. Why do we need to use sum? Think about it on your own. Okay. And for backward, we catch some values like this, and we return out. And how do you calculate backward? H and target from our cache. Reshape the out. You just flatten the out. The target now becomes d out times h. self-embed, backward, target, W. DH now becomes D out times target W. And we return DH. Okay, that is the implementation of embedding that. And the last thing we need to implement is class unigram sampler. Self corpus, power, sample size. Self sample size, the sample size, self cap size, none, self word P, none. For count, we need to count the number of each word. We're going to import collections. For count, we're going to use collections counter. For word ID in corpus, we're going to count the number of each word like this. And after that, we can manipulate the vocab size. Like this. And this word P is to calculate the probabilities of each word. We first put counts, the number of counts there. And what we are going to do is to turn this into a probability. We first power. And the next thing is normalize. In this way, this word P contains the probabilities of each word. Okay, the next job we need to do is get negative sample. Fetch side, shape 0. In this negative sample, we're going to store the sampled negative type. Okay, 4 in range. Fetch size. And after we sample the negative samples, we're going to return negative sample. Okay, try to implement this part on your own. This is our next PPP exercise. Before you move on, think about other implementations as well. Actually, I'm showing quite a lot of code blocks and try to understand each lines. Okay, see you in the next video.